February 25, 1945. A grassy field outside Tsuchiura City, Ibaraki Prefecture, Japan. Lieutenant Commander Saburo Watanabe stood at the edge of a crater, still smoking from the forced landing that had happened less than an hour before. The American fighter sat tilted at an angle, its inverted gull wings bent skyward like the arms of a fallen god, its enormous three-bladed propeller half buried in soft earth. The Corsair, Japanese pilots called it whistling death for the sound it made diving through the sky at speeds that seemed impossible. For nearly 2 years, these aircraft had dominated the Pacific skies. They hunted Zeros with systematic efficiency. They destroyed bombers before they reached their targets. They protected American carriers with such effectiveness that kamikaze pilots faced a gauntlet of fire that few survived. And now one sat intact in Japanese-controlled territory, delivered by mechanical failure, or pilot error, or simple luck. Watanabe, A, senior engineer at the Navy's First Air Technical Research Arsenal at Yokosuka, had received the telephone call at 0700 hours. An American fighter had belly-landed in a field near Tsuchiura. The pilot had been captured attempting to evade through nearby farmland. The aircraft appeared recoverable. Within 3 hours, a recovery team was assembled. Within 6 hours, they had reached the site with trucks, ropes, planking, and specialized lifting equipment. The war had taught brutal lessons about speed. American bombers came daily now. This aircraft needed to reach Yokosuka before B-29 superfortresses reduced it to scrap metal and ash. But as Watanabe circled the downed Corsair, he couldn't help pausing. This was the enemy's finest fighter, the machine that had systematically demolished Japanese air power across the Pacific, the aircraft that Japanese engineers had studied through fragments, through wreckage, through desperate intelligence reports that tried to explain how America had achieved such dominance. The bureau number painted on the fuselage read 57251. It belonged to VBF-82, a fighter-bomber squadron operating from the carrier USS Essex. The aircraft had been attacking Japanese positions near Tokyo when engine trouble forced the pilot to attempt an emergency landing. He had chosen poorly. The soft field had grabbed his landing gear and flipped him forward, but the aircraft had somehow avoided catching fire. The fuel tanks hadn't ruptured. The airframe remained structurally sound. Watanabe's assistant, Chief Petty Officer Kenji Yamamoto, approached with a crowbar and toolbox. He was a mechanic who had maintained Zeros since before Pearl Harbor, a man who could disassemble and rebuild a Nakajima Sakai radial engine blindfolded if necessary. His hands bore scars from hot metal and sharp edges accumulated over thousands of hours in maintenance hangars. "The canopy is jammed, Commander," Yamamoto reported. "We'll need to cut it free." The pilot tried to force it before running. He damaged the sliding mechanism. "Leave it for now," Watanabe ordered. "Stabilize the aircraft for transport first. The canopy can wait until we reach Yokosuka. I want this machine intact, everything intact. Every component, every system." If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The recovery team worked through the afternoon, building a stable platform beneath the Corsair's fuselage, attaching cables to lifting points, positioning planking beneath the wings. By nightfall, they had the aircraft secured on a flatbed truck, specially modified to transport captured enemy planes. Guards rode alongside, weapons ready, watching the sky for American fighters that might strafe the convoy to prevent intelligence exploitation. The journey to Yokosuka took 14 hours through roads damaged by bombing and clogged with military traffic moving supplies toward defensive positions. They traveled at night when possible, hiding beneath camouflage nets during daylight hours. American fighter patrols had grown increasingly aggressive, hunting anything that moved on Japanese roads. They reached Yokosuka on February 26th, just after midnight. The naval arsenal sprawled across hundreds of acres near Tokyo Bay, a complex of factories, testing facilities, research laboratories, and secure hangars. Before the war, it had been one of Japan's premier naval construction and repair facilities, capable of building battleships and maintaining the Emperor's fleet. Now, it served a different purpose. As Japan's offensive capabilities had crumbled, Yokosuka had transformed into a center for technical intelligence, analyzing captured American equipment in desperate attempts to understand the technological gap that had opened between Japan and its enemy. Engineers here had examined wrecked B-17, flying fortresses, captured P-51 Mustangs, and recovered fragments of American radar systems, but they had never possessed an intact Corsair. The aircraft was unloaded in Hangar 7, a secure facility surrounded by armed guards and protected by thick concrete walls capable of withstanding anything except a direct hit from the heaviest bombs. Powerful lights illuminated the interior, turning night into artificial day. A team of 15 engineers and mechanics waited, along with Admiral Goto Fumio, the Arsenal's senior technical director. Admiral Goto was 62 years old, a naval architect by training who had designed destroyers and cruisers before the war, redirected his expertise toward understanding American technology. He walked slowly around the Corsair, hands clasped behind his back, studying it with the intensity of a scholar examining an ancient manuscript. "Gentlemen," he said quietly, "we are looking at the reason Japan is losing command of the air." The statement hung in the silent hangar. No one contradicted him. Everyone present understood the reality. Japanese aircraft production had collapsed under bombing. Trained pilots had been expended in suicide attacks. The finest engineers had been conscripted or killed. Material shortages had crippled attempts to develop new designs. The Corsair represented everything Japan could no longer match. "Commander Watanabe," the admiral continued, "you will lead the technical examination. I want complete documentation, measurements, photographs, detailed analysis of every system. Pay particular attention to the engine. Intelligence reports suggest the Americans have achieved power outputs we consider theoretically impossible for a radial design of that displacement." Watanabe bowed. "Hi, Admiral. We will begin immediately." The examination team assembled around the Corsair, like surgeons preparing for a delicate operation. Each engineer had specific expertise: aerodynamics, structures, power plants, hydraulics, electronics. They would dissect this aircraft system by system, learning everything it could teach them about American engineering and manufacturing capability. Chief Petty Officer Yamamoto approached the engine cowling with practiced confidence. He had examined captured American engines before: a Pratt & Whitney R-1830 Twin Wasp from a wrecked B-26 Marauder, a Wright Cyclone from a downed B-17. Both had been impressive examples of American mass production, demonstrating manufacturing techniques and quality control that Japanese factories struggled to replicate. But the Corsair's engine was different. Even before touching it, Yamamoto could see the difference. The cowling panels were larger, suggesting something massive beneath. The exhaust stacks were positioned differently than on Japanese radials. The entire engine installation seemed more robust, more substantial, more imposing. "This is the R-2800 Double Wasp," Watanabe explained, reading from intelligence documents. Pratt & Whitney's 18-cylinder design, 2 rows of 9 cylinders each. According to American specifications, it produces approximately 2,000 horsepower at takeoff power. Yamamoto straightened, staring at his commander. 2,000 horsepower. "Commander, that must be an error. The displacement would need to be enormous to generate that much power reliably." 46 liters, Watanabe confirmed. 2,800 cubic inches in American measurements. But the power output is verified. Multiple sources confirm it. The Americans have somehow extracted extraordinary power from what is, by displacement standards, only a moderately large engine. The team worked through the night, removing the cowling panels. Each fastener was catalogued. Each panel was labelled with its position. Nothing could be lost. Nothing could be carelessly discarded. This aircraft was now more valuable than gold, more precious than ammunition, more important than fuel. It contained knowledge that might help Japan survive the coming invasion. As the engine emerged from its cowling, a collective silence fell across the hangar. Even engineers who had examined dozens of aircraft engines, who had designed and built Japanese power plants, who understood the theoretical principles of thermodynamics and combustion, stopped and stared. The R2-800 double Wasp was magnificent. The engine sat massive and gleaming under the harsh worklights, its cylinders arranged in two perfect rows around a central crankcase. Each cylinder was identically machined, identically finished, identically assembled. The cooling fins covering each cylinder head were cut with extraordinary precision, thin and closely spaced, obviously machined rather than cast. The metalwork demonstrated manufacturing capability that exceeded anything in Japanese production, but it was the size that struck everyone most forcefully. The engine's diameter measured over 48 inches, making it substantially wider than the Nakajima Sakai that powered the Zero. The crankcase alone appeared heavier than an entire Japanese fighter engine. The accessory section bristled with equipment: magnetos, fuel pumps, oil pumps, generators, hydraulic pumps, all integrated into a compact assembly that suggested sophisticated systems engineering. Yamamoto stepped closer, running his hand along one of the cylinder barrels. The metal was cool beneath his fingers, smooth and perfectly finished. He tapped it gently with his knuckle. The sound was solid, dense, speaking of thick-walled construction and substantial metal. This was not the lightweight, thin-skinned engine design that Japanese practice favored. "The construction weight must be substantial," he observed. "This engine probably weighs more than our entire Mitsubishi Kinsei 14-cylinder, perhaps 900 kilograms fully equipped." "According to intelligence," Watanabe replied, consulting his notes, "the R2-800 weighs approximately 1,050 kilograms with all accessories. Nearly twice the weight of a Sakai, but it produces more than twice the power." Senior engineer Nakamura Hiroshi, a metallurgist who had spent 20 years analyzing materials and manufacturing processes, approached with measuring calipers and a notepad. He was a small man, barely 5 feet tall, with wire-rimmed glasses and hands stained permanently black from handling metal specimens. His expertise in material science had made him invaluable as Japan struggled with shortages of critical alloying elements. "Commander," he said softly, "may I examine the cylinder head?" "Proceed." Nakamura selected one of the rear cylinders, running his calipers along the cooling fins with the delicate touch of a jeweler examining diamonds. He measured fin thickness, fin spacing, fin depth. He tapped each fin lightly, listening to the sound. He examined the base metal where the fins emerged from the cylinder head forging. After 10 minutes of meticulous examination, he lowered his tools and turned to face Watanabe. His expression was troubled. "Commander, these cooling fins are machined from the solid metal of the cylinder head. The entire assembly is a single forging, and the fins have been cut using multiple gang saws working simultaneously. Look at the precision. The fin thickness is uniform across the entire head. The spacing is exactly consistent. This represents manufacturing capability we simply do not possess." "Why is that significant?" asked Lieutenant Sato, a young structural engineer new to the team. Nakamura gestured to the cylinder head. "Because machining cooling fins is extraordinarily expensive and time-consuming. It requires specialized equipment, skilled operators, and wastes substantial material. Japanese practice uses cast fins or forged fins specifically because they're faster and cheaper to produce. But cast fins are thicker and less efficient at heat dissipation. Forged fins are better but still inferior to machined fins. The Americans chose performance over production cost," Watanabe concluded. "Not just performance over cost," Nakamura corrected. "They chose performance and accepted the cost because their manufacturing capability allows them to machine these components at scale. Look at the finish quality. This isn't a handcrafted prototype. This is series production. The Americans are manufacturing engines with this level of precision as standard production practice." The implications settled across the team like ash from a funeral pyre. Japan's aircraft engine factories employed skilled craftsmen who hand-fitted components to achieve acceptable tolerances. American factories had apparently eliminated the need for hand-fitting through superior machine tools and quality control. They could produce precision components at volume, maintaining standards that Japanese practice required individual artisans to achieve through patient labor. "Let us continue the examination," Watanabe directed, pushing through the growing realization of how far Japanese industry had fallen behind. "Remove the reduction gear housing. I want to see the propeller drive mechanism." The reduction gear housing was held by 24 bolts arranged in a circle around the engine's front face. The team removed them methodically, supporting the heavy housing with a chain hoist as the final fasteners came free. When they lifted it away, the complex gear train inside was revealed. Master Sergeant Koizumi Takeshi, a propulsion specialist who had designed cooling systems for Japanese engines, leaned close to examine the gearing. His breath caught in his throat. "Commander, this is a two-stage planetary reduction system. I see the sun gear here and the planet gears mounting in this carrier, and then a second stage reduction. The reduction ratio must be approximately 0.42 to 1, meaning the propeller turns at less than half the crankshaft speed. Is that unusual?" "It's brilliant," Koizumi breathed. By reducing the propeller speed in 2 stages, they can use a very large propeller for excellent efficiency, while running the engine at high crankshaft speeds for maximum power output. The planetary design distributes the massive torque loads across multiple gear teeth simultaneously, preventing the gear tooth failures that plague our reduction drives. He pointed to the gear teeth. "Look at the surface finish. These gears are ground to final dimensions after heat treatment, not just cut and hardened. The Americans have grinding machines capable of producing these complex, curved surfaces with this level of precision. We can cut gears, we can harden them, but grinding them to final dimensions after hardening requires machine tools we simply don't have in production." Every revelation brought fresh understanding of the chasm between American and Japanese manufacturing. It wasn't that Japanese engineers lacked knowledge. Many in this room had studied in America before the war. They understood planetary gear systems. They knew about surface grinding. They recognized quality machining when they saw it. But knowing the theory and possessing the industrial capability to implement that theory at scale were completely different challenges. Japan's machine tool industry had been adequate for peacetime production of small batches. American industry had been designed from the beginning for mass production, for high-volume manufacturing, for consistent quality across thousands of identical components. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. As dawn approached, the examination team had documented the external characteristics of the R2-800. They had measured dimensions, photographed components, sketched assemblies, and recorded observations in meticulous detail. But they hadn't yet attempted to disassemble the engine itself to examine the internal components. That would begin today. Admiral Goto returned at 0800 hours, accompanied by Captain Yoshida Hideaki from the Imperial Navy's Aviation Bureau. Yoshida was responsible for aircraft procurement and had direct authority over engine development programs. His presence indicated that senior leadership wanted immediate intelligence from this examination. "Gentlemen," the Admiral began without preamble, "what have you learned?" Watanabe stepped forward with his preliminary notes. "Admiral, we have confirmed that the R2-800 represents manufacturing capability substantially superior to our own. The engine demonstrates precision machining, sophisticated reduction gearing, and material science that exceeds our current standards. We estimate the power output at approximately 2,000 horsepower, possibly more with water injection." 2,000 horsepower, Captain Yoshida repeated, slowly. "Our finest engine, the Nakajima Homare, produces approximately 1,800 horsepower, and it does so unreliably with constant overheating problems. How have the Americans achieved this additional power?" "We don't know yet, sir. We need to disassemble the engine completely. But based on external examination, I suspect several factors. First, The Americans are using superior aluminum alloys with better heat resistance and strength. Second, their precision manufacturing allows tighter tolerances and better sealing, reducing power losses. Third, their fuel quality is likely superior, allowing higher compression ratios without detonation. And fourth, their supercharger design appears more sophisticated than ours. Yoshida nodded grimly. How long to complete the examination? 2 weeks minimum for complete disassembly, measurement, and analysis. Possibly 3 weeks if we discover components that require detailed metallurgical testing. You have 1 week, Admiral Goto interjected. The Americans are bombing our facilities daily. We cannot guarantee this hangar will survive 2 weeks. Document everything as quickly as possible. Priority to the supercharger, the reduction gear, and the crankshaft assembly. Those are the components we struggle most to manufacture reliably. Hi, Admiral. The pace of examination accelerated. Teams worked in shifts around the clock, sleeping in bunks adjacent to the hangar, eating meals brought from the Arsenal cafeteria, living inside the secure facility to prevent delays from air raid warnings. The constant threat of B-29 raids meant they could not waste a single hour. By day 3, they had removed the engine from the aircraft and mounted it on a specialized stand that allowed complete access to all sides. The Corsair's engine mount was surprisingly sophisticated, with rubber isolation bushings that reduced vibration transmission to the airframe. Japanese mounts typically used rigid connections, accepting higher vibration levels to save weight and complexity. Another example of American design philosophy, Nakamura observed. They accept additional weight and complexity to improve crew comfort and reduce fatigue. We accept discomfort to save weight and simplify production. Neither approach is wrong, but theirs requires better manufacturing capability to implement. The disassembly began with the accessories mounted to the rear of the engine. Fuel pumps, hydraulic pumps, generators. Each component was removed carefully, labeled meticulously, and photographed from multiple angles. Even these auxiliary systems demonstrated superior American engineering. The fuel pump used close-tolerance components machined to standards that prevented internal leakage. Japanese fuel pumps frequently leaked, requiring frequent maintenance and replacement. The American design appeared capable of thousands of hours of operation without servicing. The hydraulic pump was a sophisticated variable displacement design that could adjust pressure automatically based on system demand. Japanese hydraulic systems used fixed displacement pumps with pressure relief valves, a simpler but less efficient approach. The American system saved power and reduced heat generation. On day 4, they began disassembling the actual engine internals. This required removing the cylinder assemblies from the crankcase, exposing the 2-row crankshaft inside. The work proceeded with surgical precision. Every bolt's torque was noted. Every gasket's condition was recorded. Every clearance was measured with precision gauges. When the first cylinder came free, Nakamura immediately began examining the piston and rings. He set up a measurement station with micrometers, calipers, and specialized gauges designed to measure bore wear and ring tension. For the next hour, he worked in concentrated silence, occasionally muttering to himself as he recorded measurements. Finally, he looked up, his expression showing barely contained amazement. "Commander Watanabe, you need to see this." The senior engineer approached, followed by half the examination team. Everyone sensed that Nakamura had discovered something significant. "This piston," Nakamura said, holding it up to the light, "is made from an aluminum alloy I cannot identify. The material is lighter than our standard aluminum, but clearly stronger, based on the minimal wear despite what was probably hundreds of flight hours. Look at the piston rings. They show almost no wear. The cylinder walls show no scoring, no excessive wear, nothing indicating impending failure." He placed the piston carefully on a cloth. "The Americans have developed aluminum alloys superior to anything we're currently using. I suspect they've perfected aluminum zinc alloys or discovered new heat treatment processes. Either way, their pistons can withstand higher temperatures and higher pressures than ours without degradation." This alone accounts for a substantial portion of their power advantage. Can we replicate it? Watanabe asked. Nakamura hesitated. Theoretically, yes, but practical replication requires access to alloying elements we don't have. Zinc, magnesium, copper in specific ratios. Our supply lines have been cut. We're using substitute materials of inferior quality. Even if I gave our metallurgists the exact formula tomorrow, our factories couldn't produce it reliably. The examination of the crankshaft revealed another marvel of American engineering. The crankshaft was a multi-piece assembly, with the two-row master rod configuration allowing all 18 cylinders to connect to a single crankpin per cylinder. The machining was extraordinary. The bearing surfaces were ground to near-mirror finishes. The balance weights were precisely calculated and positioned. The entire assembly was obviously designed for reliable operation at high power outputs for extended periods. Japanese crankshafts frequently failed under sustained high-power operation. The Nakajima Homare, Japan's most powerful production engine, had earned a reputation for catastrophic failures when pilots pushed it to maximum power. The crankshafts would crack, the bearings would fail, oil pressure would drop suddenly, followed by engine seizure. The R-2800's crankshaft showed no signs of such weaknesses. The bearing journals displayed minimal wear despite whatever operational history this engine had experienced. The fillet radii where the journals met the crank webs were carefully designed to eliminate stress concentrations. The materials and heat treatment appeared flawless. This represents decades of development, Chief Yamamoto observed, running his hand along the crankshaft. The Americans didn't achieve this overnight. This is institutional knowledge, accumulated experience, engineering lessons learned over thousands of engines and millions of operating hours. We're trying to compress that learning into months because we started the war without it. By day 6, they had reached the supercharger, the component that compressed incoming air to increase power at altitude. This was the most critical system for understanding the Corsair's high-altitude performance. Japanese superchargers had always lagged behind American and British designs, limiting the effectiveness of Japanese fighters above 20,000 feet. The R-2800 used a two-stage supercharger, meaning the air passed through two separate compression stages before entering the cylinders. The first stage was a moderate compression ratio, and the second stage provided additional compression when needed at high altitude. Between the stages sat an intercooler, a heat exchanger that cooled the compressed air to increase its density. Senior engineer Tanaka Masaru, a supercharger specialist who had spent 5 years trying to improve Japanese designs, spent an entire day examining this system. He measured impeller dimensions. He studied the diffuser, vanes. He analyzed the intercooler construction. He examined the automatic control mechanism that shifted between single-stage and two-stage operation based on altitude. Finally, on the evening of day 6, he delivered his assessment to the gathered team. Gentlemen, this supercharger represents everything we've tried to achieve, but failed to implement. The two-stage design provides excellent power at altitude without sacrificing low-altitude performance. The intercooler is beautifully engineered, providing effective cooling without excessive pressure loss. The automatic controls work seamlessly, requiring no pilot intervention. He paused, choosing his words carefully. But what impresses me most is the precision of the machining. Look at these impeller blades. They're machined to extremely tight tolerances. The surface finish is excellent. The blade profiles are carefully calculated for optimal aerodynamics. This is not trial and error engineering. This is sophisticated, computational design combined with precision manufacturing. Can we build this? Admiral Goto asked from the doorway. He had entered silently, listening to Tanaka's presentation. Not with our current manufacturing capability, Admiral. We lack the machine tools. We lack the materials. We lack the testing facilities. Even if we had perfect blueprints, our factories couldn't replicate this with sufficient precision to make it work reliably. The Admiral nodded slowly. He had expected this answer. Continue the examination. I want every measurement, every material specification, every design detail documented. Even if we cannot build this today, we may be able to use this knowledge in the future. The final days of examination focused on measuring and documenting every component: piston dimensions, valve dimensions, connecting rod lengths, cylinder spacing, crankshaft stroke, compression ratios, cam timing, port sizes. Everything was recorded in detailed notebooks that would be stored in secure archives. On the evening of Day 7, Watanabe compiled his findings into a comprehensive technical report. The document ran to 87 pages with attached drawings, photographs, and material analysis reports. He worked through the night, writing the executive summary, knowing that senior Navy leadership would read only the first few pages before making decisions about resource allocation and development priorities. At 0600 hours on March 5, 1945, he presented his conclusions to Admiral Goto, Captain Yoshida, and a group of senior engineers from Navy Air Technical facilities across Japan. Gentlemen, Watanabe began, the examination of the captured F-4U Corsair and its R-2-800 engine has revealed the technical foundations of American air superiority. I will be direct. The Americans have not achieved victory through revolutionary breakthrough technology. They have achieved victory through superior execution of conventional engineering supported by manufacturing capability that exceeds ours by factors of 5 to 10. He displayed a chart showing comparative specifications. The R-2-800 produces 2,000 horsepower from 46 litres of displacement. This represents 0.78 horsepower per cubic inch. Our finest engine, the Nakajima Homare, produces 0.60 horsepower per cubic inch and does so unreliably. The American advantage comes from superior materials, superior precision, superior quality control, and superior fuel. What specifically must we improve? Captain Yoshida asked. Everything, sir. Our aluminum alloys are inferior. Our precision machining is inferior. Our heat treatment processes are inferior. Our fuel quality is inferior. Our superchargers are inferior. Our reduction gears are inferior. Our quality control is inferior. The Americans have not made one breakthrough. They have made 100 small improvements, each building on the others, creating a comprehensive advantage we cannot quickly overcome. Watanabe continued. The R-2-800 is not a super weapon. It is an extremely well-engineered and precisely manufactured conventional engine. Every component reflects decades of accumulated experience. Every design choice reflects lessons learned from thousands of earlier engines. Every manufacturing process reflects investment in machine tools and training that we never made. He paused, letting the implications sink in. The Americans started their aviation engine industry in the 1920s. They learned from European designers. They licensed designs from Britain and France. They hired experienced engineers from abroad. They invested in research facilities, testing equipment, and specialized machine tools. By 1941, they had 20 years of continuous development, creating institutional knowledge we lack. Japan started later. We licensed engines from foreign manufacturers but never developed the compulus, supporting industrial infrastructure. When the war began, we tried to compress 20 years of development into 2 years. We failed. This engine proves how completely we failed. Admiral Goto stood slowly. Commander Watanabe, your assessment is brutally honest. I appreciate your directness. What do you recommend? Admiral, we cannot replicate the R-2-800 with our current industrial base. Even if we had perfect blueprints, we lack the materials, the machine tools, and the skilled workforce. Our factories are being destroyed by American bombing. Our supply lines are cut. Our best engineers are being killed or conscripted. Watanabe took a deep breath. My recommendation is to focus all remaining resources on defending the homeland using existing designs we can manufacture reliably in dispersed facilities. Stop attempting to develop wonder weapons. Stop trying to match American technology. Accept that we will fight with inferior equipment and find tactics to compensate. The silence in the room was absolute. Watanabe had just recommended accepting technological defeat, acknowledging that Japan could not match American industrial might, admitting that the war was already lost on the engineering and manufacturing front, even if battles still raged. Captain Yoshida broke the silence. "Your honesty will not make you popular, Commander, but you are correct. We have been chasing American capability instead of optimizing for our actual situation. We need fighters we can build in cave workshops with hand tools, not sophisticated engines requiring specialized factories." He looked around the room. "Gentlemen, the era of Japanese technological parity has ended. From this point forward, we are the underdog fighting with improvisation and determination against an enemy with overwhelming industrial superiority. Commander Watanabe's examination of this engine has taught us that lesson clearly." The report spread through Japan's aviation establishment like a contagion. Copies reached the Army's Aviation Technical Research Institute at Tachikawa. Engineers at Mitsubishi Heavy Industries in Nagoya read it with growing dismay. Nakajima Aircraft Company's design bureau studied the specifications and recognized their own failures reflected in American success. But the reaction that mattered most came from the engineers themselves, the men who had dedicated their careers to designing aircraft engines, who had believed that Japanese craftsmanship and dedication could overcome any material disadvantage. For them, the R2-800 examination represented a moment of profound psychological reckoning. On March 8, 1945, 3 days after Watanabe's presentation, a group of senior Japanese engine designers gathered at a secure facility outside Tokyo. The meeting had been called by the Navy's Aviation Bureau to discuss potential responses to the intelligence from the captured Corsair. The attendees represented the cream of Japanese aviation engineering talent. Nakajima's chief engineer for the Homar program, Nakagawa Ryoichi, arrived carrying a worn leather briefcase containing years of development reports and failure analyses. He was 43 years old, educated at Tokyo Imperial University, holder of numerous patents for supercharger improvements. He had spent the last 4 years trying desperately to make the Homar reliable enough for combat operations. The Homare engine, designated Ha-45 by the Army and NK-9 by the Navy, represented Japan's most ambitious attempt to create a high-powered radial engine. With 18 cylinders arranged in 2 rows and a displacement of 55.9 litres, it was actually larger than the R2-800. On paper, it should have produced comparable power. In practice, it was a maintenance nightmare. The engines overheated constantly, cylinder barrels cracked under stress, connecting rods failed catastrophically, spark plugs fouled after just hours of operation. Pilots described the Homar as unreliable, underpowered, and dangerous. Aircraft equipped with Homar engines frequently returned to base on reduced power or didn't return at all. Nakagawa had spent countless hours analyzing failures, redesigning components, testing modifications. He understood intellectually what was wrong. The Japanese had designed an engine for power output that their manufacturing capability couldn't reliably produce. Tolerances that looked acceptable on paper translated to catastrophic failures under operational stress. Materials that tested adequately in laboratories degraded rapidly under combat conditions. But understanding the problem intellectually and accepting it emotionally were different challenges entirely. Mitsubishi's representative was Kubo Katsuhiko, designer of the Kasei engine that powered bombers and some fighters. The Kasei was more reliable than the Homare, but produced only about 1,850 horsepower maximum, and it was physically enormous, with a diameter over 52 inches. It worked, but it represented older design philosophy, emphasizing reliability over power density. Kubo had read Watanabe's report 3 times, studying every specification, every measurement, every observation about American manufacturing practice. Each reading had deepened his understanding of how far Japanese engine design had fallen behind. The meeting began at 1400 hours in a concrete bunker designed to survive anything except a direct bomb hit. The attendees sat around a large wooden table scarred by cigarette burns and coffee stains, physical evidence of hundreds of previous engineering discussions conducted in this same room. Captain Yoshida opened the meeting with characteristic bluntness. Gentlemen, you have all read Commander Watanabe's report on the American R2-800 engine. I want your professional assessment. Can we build an equivalent engine? The silence stretched for nearly 30 seconds. Finally, Nakagawa spoke. Captain, the honest answer is no, not with our current industrial situation. The R2-800 requires manufacturing precision we cannot maintain. It requires materials we cannot obtain. It requires quality control we cannot implement across our dispersed production facilities. He opened his briefcase and extracted a thick document. This is the complete failure analysis for Homar engines produced in the last 6 months. Of 218 engines delivered to operational units, 93 experienced major failures, requiring complete replacement before reaching 100 hours of operation. That represents a 43% failure rate. The number hung in the air like an accusation. 43%. Nearly half of all engines failed catastrophically, almost immediately. Why? Yoshida demanded. You designed the Homare. You understand the principles. The displacement is adequate. The configuration is sound. Why does it fail? Nakagawa's voice remained steady, but his hands trembled slightly as he spoke. Because our factories cannot maintain the required tolerances, Captain. We designed the Homare for precision assembly using skilled craftsmen working with the finest tools. Then, American bombing destroyed our main production facilities. We dispersed production to smaller workshops, cave factories, facilities using older machine tools operated by workers with minimal training. He gestured to the report. The Homare has 87 major components that require tolerances within 0.02 of a millimeter. Our main factory at Musashi could achieve those tolerances consistently. Our dispersed facilities achieve them occasionally, when skilled workers carefully adjust each component by hand. But mass production requires consistency. American factories produce components to specification automatically. Our factories produce components that must be individually fitted, and we no longer have enough skilled fitters. Kubo, from Mitsubishi, added his perspective. The Kase is more reliable precisely because we designed it with looser tolerances, accepting lower power density to enable production in less sophisticated facilities. It's not elegant engineering, it's compromise engineering, but compromise we can actually manufacture. The Americans don't compromise? Yoshida asked. Oh, they compromise, Kubo replied, but they compromise differently. They accept additional weight for reliability. They accept higher production costs for better quality. They accept complex manufacturing processes because their factories can handle that complexity. Their compromises assume abundant resources and sophisticated manufacturing. Our compromises assume scarcity and simplified production. Nakagawa leaned forward. Captain, may I speak candidly? Please. The R2-800 represents 20 years of continuous development by Pratt & Whitney. That company employs tens of thousands of workers. They have dedicated testing facilities where engines run for thousands of hours under controlled conditions. They have metallurgical laboratories analyzing failure modes. They have teams of engineers focused solely on improving specific components. He paused, choosing his words carefully. Pratt & Whitney's engineering staff alone probably exceeds the total number of engine designers in all of Japan. Their annual research budget exceeds our entire national aviation engine development spending. They can afford to build 50 prototype engines to test one new feature. We build 3 prototypes if we're fortunate, and we rush them into production because we're desperate for any improvement. You're saying we cannot match them? I'm saying we never could match them, Captain. Not in industrial capacity, not in research infrastructure, not in accumulated experience. The R2-800 proves what we should have understood from the beginning. Industrial war is, and won by industrial capability, not by courage or determination or even technical brilliance. Another engineer, Tanaka from the Army's Research Institute, interjected. Surely we can learn from their design? Copy their innovations? We've been trying, Nakagawa replied tiredly. Every crashed American engine gets examined. We measure everything. We analyze materials. We study design features. And then we try to incorporate improvements into our engines. Do you know what happens? He didn't wait for an answer. The improvements require manufacturing precision we don't have, or they require materials we can't obtain, or they work in isolated testing but fail when integrated with other components because the entire system must be designed together, not piece by piece. Nakagawa stood and walked to a chalkboard mounted on the bunker wall. He began sketching an engine cross-section from memory, his hand moving with the practiced confidence of someone who had drawn this diagram thousands of times. The R2800 works because every component supports every other component. The pistons are designed for the specific cylinder temperatures generated by that combustion chamber shape with that fuel quality. The piston rings are designed for those specific cylinder wall finishes. The crankshaft is designed for the loads generated by those connecting rods at those operating speeds. He tapped the diagram with the chalk. If we copy the piston design but use our inferior aluminum alloy, it fails. If we copy the ring design but install it in cylinders with rougher wall finishes, it wears prematurely. If we copy the crankshaft design but manufacture it with our heat treatment processes, it cracks. Every component depends on every other component meeting specifications. And American factories can produce all those components to specification consistently, Yoshida concluded. Yes, Captain, that is the fundamental difference. American engineering isn't better in the mating, abstract sense. Their engineers aren't smarter than ours, but their industrial system can execute sophisticated designs reliably at scale. Our industrial system cannot, especially after 3 years of bombing has destroyed our most capable factories. The discussion continued for 3 hours, ranging across technical details, manufacturing limitations, material shortages, and strategic implications. The conclusion was inescapable. Japan could not build engines comparable to the R2800. Not now. Probably not for decades, even if the war ended and reconstruction began immediately. That evening, Nakagawa returned to his small office at the Nakajima facility. The building had been damaged by bombing, and his office window was covered with boards where glass had once been. His desk was piled with reports, drawings, calculations, all representing years of effort trying to make Japanese engines competitive with American designs. He sat in the darkness for a long time, thinking about the R2800. Not about the technical specifications, not about the manufacturing processes, but about what that engine represented at a deeper level. The R2800 was the product of a society that valued systematic improvement over individual brilliance, a society that invested in infrastructure, in education, in research facilities and testing equipment, a society that understood that industrial capability required decades to develop and couldn't be created through force of will or desperate necessity. Japan had tried to fight an industrial war with craftsman values, individual skill, personal dedication, spiritual strength. These things mattered, but they couldn't overcome systematic industrial superiority. One brilliant engineer working 18-hour days couldn't match 50 competent engineers working regular shifts with proper equipment and adequate resources. The realization was devastating. Everything Nakagawa had believed about Japanese, exceptionalism, about the superiority of Japanese craftsmanship and dedication, crumbled when confronted with the reality of the R2800. The Americans hadn't won through superior culture or greater determination. They had won through better organization, more systematic thinking, and massive investment in productive capacity. The psychological impact of the Corsair examination extended far beyond the handful of engineers who had directly studied the engine. As word spread through Japan's technical community, a quiet desperation took hold. Everyone understood that the war was lost. The question was what lessons to preserve for whatever future Japan might have after defeat. At Yokosuka, Commander Watanabe had moved on to examining other components of the captured Corsair, the hydraulic systems, the electrical systems, the flight control mechanisms, Every system told the same story of sophisticated engineering executed with precision manufacturing. The hydraulic system used aluminum tubing throughout, brazed with perfect joints that showed no signs of leakage. Japanese hydraulic systems frequently leaked, requiring constant maintenance and replacement of rubber seals that degraded rapidly. The American system was designed for long-term reliability with minimal servicing. The electrical system used standardized connectors throughout, allowing quick replacement of damaged components. Japanese electrical systems used custom connections for each application, making field repairs difficult and time-consuming. The American approach required more initial engineering and more sophisticated manufacturing, but it made maintenance dramatically easier. The flight control cables were made from stainless steel, immune to corrosion even in the harsh maritime environment where carrier aircraft operated. Japanese control cables were plain steel, treated with oil or grease for corrosion protection. The treatment wore off quickly, and cables corroded, requiring frequent inspection and replacement. Every detail reinforced the same lesson. American designers assumed their aircraft would be maintained by relatively inexperienced mechanics in field conditions with limited tools. They designed for ease of maintenance, for durability, for resistance to abuse and neglect. Japanese designers assumed careful maintenance by skilled technicians using proper tools in equipped facilities. The American assumption proved more realistic for actual combat operations. On March 17, 1945, American carrier aircraft struck Yokosuka Naval Arsenal as part of the intensifying campaign against Japanese military installations. The raid came at dawn, with waves of Corsairs, Hellcats, and Avengers attacking from multiple directions. The arsenal's anti-aircraft guns opened fire, filling the sky with black bursts of flak. Japanese fighters rose to intercept, but they were too few and too late. The American formations swept over the facility, dropping bombs and rockets with systematic precision. Hangar 7, where the captured Corsair had been examined, took 2 direct hits from 500-pound bombs. The structure collapsed, killing 3 engineers and destroying most of the documentation that hadn't yet been removed to secure storage. The Corsair itself was damaged beyond repair, its fuselage broken, its wings torn, its precious R2-800 engine buried under tons of rubble. Commander Watanabe survived because he had been in a different building reviewing photographs. When he reached Hangar 7 through smoke and debris, he found only destruction. Rescue teams were pulling bodies from the wreckage. Engineers stood watching helplessly as decades of knowledge literally burned before their eyes. But the examination had been completed. The measurements had been recorded, the photographs had been taken, copies of the technical report existed in multiple secure locations. The knowledge extracted from that single captured aircraft had been preserved even if the aircraft itself was destroyed. That knowledge, however, was of limited immediate utility. Japan couldn't build engines like the R2-800, couldn't manufacture components to those tolerances, couldn't obtain the materials required, couldn't maintain the quality control necessary. The technical intelligence was perfect. The industrial capacity to exploit it didn't exist. In the final months of the war, Japanese engineers worked desperately on simplified designs that could be manufactured in dispersed facilities with minimal tooling. They designed engines that could be assembled by unskilled workers using hand tools. They accepted terrible reliability and poor performance because those were the compromises necessary for production under bombardment. The Showa Ha-43 was one such design, an 18-cylinder radial intended to produce 2,200 horsepower. It existed mostly as drawings and a few hand-built prototypes. The manufacturing infrastructure needed for production had been destroyed before series production could begin. The Mitsubishi Ha-214 was another, a massive engine designed to power interceptors that would destroy B-29 formations. It achieved some success in limited testing, but never reached operational squadrons in meaningful numbers. American bombing had seen to that. By August 1945, Japan's aircraft engine production had collapsed completely. Factories lay in ruins, skilled workers had been killed or conscripted, materials were exhausted, The sophisticated machine tools required for precision manufacturing had been destroyed or worn beyond use with no possibility of replacement. When Japan surrendered on August 15, 1945, the aviation industry ceased to exist. The occupation authorities prohibited all aircraft research and development. Factories were dismantled. Design bureaus were closed. Engineers who had spent careers advancing Japanese aviation technology found themselves unemployed, their expertise suddenly worthless in a defeated nation. Many of those engineers, including Nakagawa Ryoichi from Nakajima, would eventually find work in Japan's automotive industry. The lessons they had learned about precision manufacturing, about quality control, about systematic improvement, would influence Japanese car and motorcycle production in the post-war decades. The industrial philosophy they had tried unsuccessfully to implement in aircraft engines would prove extraordinarily successful in automotive applications. But that was future redemption. In August 1945, those engineers faced only the wreckage of their dreams and the undeniable proof that individual brilliance couldn't overcome systematic industrial inferiority. The captured Corsair's final contribution came not during the war, but after it ended. American technical intelligence teams fanned out across Japan, cataloguing what remained of Japanese aviation research facilities. At Yokosuka, they found Watanabe's reports, including his detailed examination of the R2-800 engine. Reading those reports, American engineers gained insight into how Japanese industry had viewed American technology. They saw themselves through enemy eyes and recognized aspects of their own industrial philosophy that they had taken for granted. The systematic approach to quality control, the investment in precision machine tools, the emphasis on making components interchangeable and maintenance procedures standardized. These weren't revolutionary insights to American engineers, but seeing them highlighted in Japanese analysis reinforced their value and justified the massive investments that had made them possible. The captured Corsair had taught lessons to both sides, though the lessons were very different. For Japanese engineers, the lesson was humbling. Industrial war required industrial capability that couldn't be improvised or overcome, through determination alone. Technology mattered, but the ability to manufacture technology at scale with consistent quality mattered more. Individual brilliance was valuable, but systematic competence was decisive. For American engineers, the lesson was more subtle. Their victory hadn't come from revolutionary breakthroughs or wonder weapons. It had come from doing ordinary things extraordinarily well, from investing in infrastructure, from standardizing processes, from training workers properly, from maintaining quality control even under pressure to produce quickly. The R2-800 wasn't a marvel. It was a competently designed engine, manufactured with excellent precision using good materials. That this represented insurmountable superiority to Japan said less about American genius than about the cumulative advantage of systematic investment in industrial capability. Decades after the war, Watanabe would write his memoirs, including detailed recollections of examining the captured Corsair. His account emphasized the psychological impact more than the technical details. The growing realization that Japan had never had a chance in industrial war against America. The desperation of trying to extract useful intelligence from an engine Japan couldn't hope to replicate. The bitter recognition that courage and skill couldn't compensate for systematic industrial inferiority. We examined the R2-800, he wrote, hoping to find a secret we could steal, a weakness we could exploit, a lesson that could change our fortunes. Instead, we found only confirmation of what we should have known before the war began. Industrial war is decided by industrial capacity. We had chosen to fight an enemy whose factories could produce more in 1 month than we could produce in 1 year. No amount of engineering brilliance could overcome that fundamental imbalance. The Corsair that had force-landed in a field near Tsuchiura on February 25, 1945, had been one aircraft among thousands that American factories produced. Its loss was statistically insignificant to American military operations. The pilot who had crashed it was rescued after the war from a POW camp and returned home to resume his life. But for Japanese engineers, that single aircraft had become a symbol of everything they couldn't achieve. a reminder of industrial realities they couldn't overcome, a teacher whose lessons were simultaneously invaluable and utterly discouraging. The Pratt & Whitney R2-800 Double Wasp would continue in production until 1960, long after the war ended. More than 125,000 engines would be built, one of the largest production runs of any aircraft engine in history. They would power airliners, military transports, firefighting aircraft, and restored warbirds flying at air shows decades after their initial design. The engine's longevity testified to the soundness of its fundamental design and the quality of its execution. Engines built in 1944 would still be running reliably in the 21st century, maintained by enthusiasts who appreciated the craftsmanship and engineering excellence represented in every precisely machined component. For the Japanese engineers who had examined one such engine in March 1945, that longevity would have been unsurprising. They had seen the quality of materials, the precision of manufacturing, the sophistication of design. They had understood immediately that this was an engine built to last, manufactured by a nation that thought in terms of decades rather than desperate months. The examination of the captured Corsair and its engine had revealed truth that no amount of propaganda could obscure. American industrial might wasn't an illusion or temporary advantage. It was the product of systematic investment, accumulated experience, and organizational capability that Japan couldn't match. Individual Japanese engineers might equal or exceed individual American engineers in raw talent, but talent distributed across inadequate infrastructure couldn't compete with competence supported by industrial excellence. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.